Question 12, this is a canopy which comprises 3 cantilever arms which sit on a fascia beam which is fixed at the ends rotationally, and this beam we're going to look at 2 options for the beam. It's got a load of P which is the maintenance load, and the L is the L of the cantilever, so we're looking at torsion which is TL, which is exerted on the fascia beam, and this is split in the middle, T over T, T over T to the supports, and we're going to look at the rotation of this, and the section is given for the cantilever, which is a average 150 by 12 thick plate. It's tapered, it goes from 200 to 100, but we believe this stage in the design that at 150 take the average would be adequate for the properties, and it's got the shear modulus of steel, the modulus of steel, and the IXX for the beams which are relevant. In the first case we're going to look at a rolled hollow section, which is a hollowed section. The second case is a channel, which is an open section. The hints are in figures 2.9.8, 2.9.9 and 2.3.2, and we'll go on to the next section. Question 12a, and we set up the beam, which is a 4 metre span, and it's got the arm in the middle generating a torsion of 1 kilonewtons at 1.5 metres away, and the torsion is halved to the ends of the beams. So just working out the torsion at the end of the middle arm, it's 1 times 1.5, which is 1.5 kilonewton meters, with half of this to each end of the beam, 0.75, classic torsion distribution. Figure 2.9.4 and 2.9.8, the rotation is given by TL over GJ. G is 78 E3 newtons per millimeter squared, and the L distance is half the span in this particular instance. So we put those figures in and we come up with 0.0009, 9 times 10 to the minus 4 radian. This example's referring to the rectangular hollow section. Channel is next. Question 12b. We're going to look at the rotation for the channel section. This is the section that the architect would like to have aesthetically. We've got torsionally fixed ends, and it's 200 by 90 PFC, and again setting up before, torsion is 1 times 1.5 from the previous question, and it's half of this to each end of the beam. The torsional constant for the PFC, the inertia is 18 centimeters to the 4, and putting these values in, again as I say, taking half the span of the beam, we come up with a rotation of 0.106 radians. And if you take your mind back to example 12a, it's 0.0009 radians, so the RHS is significantly lower rotation. Question 12c. We are going to compare the deflections at the tip of the tapered cantilever elements from the rotations, and we're going to obtain this by the cantilever span times the rotation. If we ignore the flexural deflection of the tapered arm, which is going to be relatively low, I times L is for the RHS section, gives you 1.35 millimeters. This is 9 times 10 to the minus 4 radians from 12A, and from 12B. For the PFC we've got a much higher rotation, which gives 168 millimeters. So the architect's desire for a PFC runs into problems, and we're going to have to look at an alternative design for this. Just a footnote for some of you that might be wondering, on the cantilever, if we've considered, or we need to consider, lateral torsional buckling, because there's no particular restraint to the compression zone in the tapered beam. The glazing is in the top, that would help restrain things, but not underneath. So why not? Well, it's a low moment, it's a relatively thick section of 12 millimeters, and we are in the early concept design stages. However, it is possible to do rudimentary checks, and we're going to do a quick check just for comfort. So we separate the beam into tension and compression zones, and the depth overall is 200 millimeters, and we're going to say the lever arm, we're just going to say that's 100 millimeters. That's roughly 50 millimeters from top and bottom. And the ultimate moment is a 1.5 factor, let's say, times 1.5, that's 2.25 kilonewton meters, and the compression force is M over LA, which is 22.5 kilonewtons. So the next stage is we're going to isolate the compression zone, the tapered beam, by means of strut analogy. So let's draw out again the beam, and there's your compression zone, and let's isolate this part of it, and we will decide what the depth of it's going to be. So let's go and isolate it as if it was a strut. This is a conservative estimate. So we've got 22 kilonewtons. We're going to assume it's 75 millimeters deep. I mean, it's worth being conservative at this stage. It's not going to be any more than half the depth, it's going to be less than that. It's 12 millimeters thick, and in the chapter 2.7, page 78 in the book, we're going to do an Euler buckling check, PCR, and you could also do a compression check, just standard bending. So the I value we've given 75 cubed times 12 over 12. We've got E of 205 times 10 to the 3. The effective length is going to be, let's say, 1.5 factor for buckling. So we multiply out 1500 by 1.5. It gives 2250 millimeters for our LE, our effective length. And we use those figures to obtain PCR, critical buckling force, and this comes out at 170 kilonewtons, which is much greater than our strut load of 22.5 kilonewtons. So we're pretty well within the safe region here, and even if we slim down the beam to 6 millimeters thick as a taper, it should work. Thank you for listening.